The plus sign, you've been using it a long time, but think about the kinds of things you've been putting it in between. Of course, you started by putting it in between numbers. You're adding numbers together, but lately we've been adding vectors together. V and W are vectors, and there's a way to add them together. That looks something like this, right? So if those are two vectors, there's a way to add them. Of course, we've also been adding matrices together. There's a way to do that. And you might remember that there's a way to add functions together. If f is a function and g is a function, then f plus g is also a function. And what's important about this plus sign in each of those cases with these different kinds of objects that we're adding together is that we have something called closure. If I add 2 and 3 together, those are two different numbers, and the result is also, of course, a number. The number 5 is a number. If I add two vectors together, I get a vector. I get a new vector. And if I add these two 2x3 matrices together, I get a 2x3 matrix. These sets are closed under this operation of addition, as we could say. Of course, if f is a function and g is a function, then f plus g is its own function. For example, if f of x is the square root of x plus 1 and g of x is sine 4x, then you know what f plus g means. It means just the algebraic addition, the sum of those two things. So what about scalar multiplication? That's another kind of thing we've been doing lately with vectors. And when I say a scalar, I mean a number. So if x is a vector, then 2x means something, and if a is a matrix, then 2a means something, and if f is a function, then 2f means something. So scalar could be any number, could be that number 2 or some other kind of number there. Each one of those things makes sense. I can multiply a vector by a number. 2 times that vector makes that other thing. And so, again, it's important that what I get is still, a vector. It's not something different. If I multiply a matrix by a vector, if I multiply a matrix by a scalar, I get another matrix. And you can multiply a function by a scalar. And again, just to give an example, if f of x is something like that function there, then the function 2f would be the function that you would obtain just by multiplying all the outputs by 2. So you could just multiply the 2 through there and you get this function. Now, in each of those examples, we keep looking at these different examples of things that I can add together and things that I can scalar multiply. And in each of these scenarios, there's some kind of concept of a zero. For example, if I'm adding vectors together, there's this zero vector, that vector -1, 2, 1. If I add that 0, 0, 0 vector to it, I still get -2, 1. That's -1, 2, 1, The idea being that that 0 vector is the thing that when I add it to other things, it doesn't change that thing. So let me ask you, what would the 0 vector be, 0 element be in the set of matrices? So is there something that you could put there in that question mark spot that if you add it to this matrix, you'll get that same matrix back? Well, the answer, of course, is you just use the matrix full of zeros, and that works just fine. That works just like the 0 vector I had on the previous slide. Now, what about functions? Is there a function that you could add to other functions? Maybe we'll call it z, that if I add it to f, I just get f back. Well, yes, it's just the obvious thing. Z of x is just the function that always produces the answer 0, and that behaves like the 0 element. So what we're talking about here is we keep talking about a collection of objects where you have some kind of, it's a set of objects, but you have some kind of idea of addition and scalar multiplication. And that addition, it kind of feels kind of like the same thing in each of those examples, but it's not exactly the same thing. Under the surface there's some kind of addition of numbers happening, but the plus sign that we keep putting in between things is a little bit different every time. It means something different. We use the same symbol, but it's a slightly different operation, right? So let me go over a few different kinds of specific vector spaces, these kinds of sets together with an addition idea and with some kind of scalar multiplication idea. Of course, there's the real numbers. That one's not very interesting. You can add them together, you can multiply them by numbers, but maybe it gets a little bit more interesting when we talk about Rn, the set of all n-dimensional vectors, which in linear algebra we like to visualize as being n by 1 matrices. Rm by n, we're going to use that to mean all the m by n matrices. So on the previous slide I had 2 by 3 matrices together. We could think of those matrices as being in the set R 2 by 3. This funny looking notation here, FRR, that's the set of all functions from the real numbers to the real number. So I had some examples in the previous slides. Just a collection of all functions, and that together makes a set, and there's a way to add them together, and there's a way to take a function and multiply it by a scalar. P sub n, that one we haven't mentioned yet, that's the set of all polynomials of degree less than or equal to n. It's important that you say less than or equal to n. It doesn't have to equal n. For example, this polynomial here, 3x squared plus 2x minus 4, is in the set called P2 because its degree is 2. But even if I had just written down 2x minus 4 without the 3x squared, that would be a different thing also in P2 because its degree is less than or equal to 2. There's another vector space called, which is the set of all infinite sequences. You've probably studied sequences at some point in your past. Those go on forever, right? Those are infinite, right? So, there is a notation, I guess sometimes we call it R infinity. And the good question is there some way to add sequences together? Is there some kind of idea of scalar multiplication? And it's basically just term-by-term addition and term-by-term scalar multiplication. But I'll let you think about how that works a little bit more. And in that set, what would the zero vector be? Or the zero element, if you want to call it that. What would it be? I think it would just be the sequence of all zeros, right? So I keep calling these things vector spaces. A vector space is a set with addition and scalar multiplication, but we need a couple more things, though, a few more things before we really give it the title of vector space. We need a few more properties we're going to agree on. First of all, we want the addition to be associative, this old rule that you remember. We want the addition to be commutative. You know, however we've defined addition, it should be associative, it should be commutative. And there should be some kind of zero element in this set. So even if I come up with some kind of bizarre examples of things that I can add together in some way, if I really want to call it a vector space, I need all these things. I need to have some kind of zero vector. Well, usually we use, you know, the regular looking number 0 for that spot. You know, we might put it in boldface to make it look a little bit different. It's not necessarily the number 0, of course, but there's some element that behaves like 0 in the set. Well, if there's some element that behaves like 0 in the set, then we can ask that everything have an inverse, something that when you add it to v, for example, then v plus that thing should be 0. And we usually think of that as being, we call it negative v, right? But that's something that when you add it to v, you get 0. There's some other properties that we need to hold. I'll just throw these up on the screen here. You would call maybe the first two the distributive property, but it's a slightly different kind of distribution happening there. And scalar multiplication has to play nicely with numerical multiplication and the third element there, property there. And the number 1, the number 1, when we multiply a vector times the scalar 1, we should just get v again. It should behave that way. So what about all these words here? Span, linear independence, basis, coordinates, and dimension. Those are all words that we've kind of seen in the context of Rn, that our favorite vector space. Do they still mean something in these other vector spaces? Well, the definitions we gave for those things like a span, the linear independence, and stuff like that, those were all definitions that were just algebraic at their heart. We didn't really specifically commit ourselves to talking about R2 or R3 in those examples, and maybe we can broaden those definitions to make sense even in a vector space like R2 by 3 or the vector space containing all functions or something like that. For example, think about P2. That's the set, again, that's the set of all polynomials of degree less than or equal to 2. What is its dimension? Can we ask that question? Well, if we want to say what its dimension is, I guess we have to have some kind of idea. What does it have a basis? Is there a basis for this set? Well, maybe that works like a basis, doesn't it? Those three vectors there, those, I keep calling them vectors because I'm kind of in the context of a vector space, but, you know, maybe I should call them polynomials. Do those three polynomials work as a basis? Well, clearly they're a spanning set. If you give me any polynomial, 2x squared plus 3x minus 5, I can make that polynomial, for example, as a linear combination of the x squared, x, and 1 in the obvious way. Now, another question is that linearly independent? And the answer is yes, and I don't think that's hard to prove, but I'll leave that up to you. And, sorry, I should have said that because of that, the dimension of that space, P2, is 3, because we wrote down 3 different vectors which span it, which were a basis. What about R2 by 2? That's also a vector space. Does it have a dimension? Well, I think this would work as a basis, right? Look at those 4 matrices there. Those 4 matrices could be combined with a linear combination to produce any other matrix, right? So they work like a basis, and they're kind of clearly linearly independent if you think about what that means in terms of the definition. What about this set? This one's a little goofy. The set of all functions from R to R, and then we ask the question, well, what's its dimension? Now we're getting into harder territory. What's a collection of functions that would produce any other function with linear combinations? And I don't think that's possible. And the answer is it isn't. It's what we call infinite dimensional. It does not have a finite basis. It's just too wild, right? There's too much variability in that. Okay, so now it's your turn. How about you try a problem here? And maybe what we should do is think about some subspaces of some of those spaces that I just described. Here's a problem. Think of these, let's let C be this matrix here. It kind of looks like the identity matrix. Note it isn't quite the identity, right? We've moved the zeros and ones around there a little bit. So let C equal that matrix. And then let's think of this set S as the set of all matrices, all the 2 by 2 matrices that commute with C. And when I say commute with C, I mean this. I mean that matrix A to commute with C means that AC is equal to CA. You know, of course, that that's not automatically true for matrices, right? Matrices don't commute necessarily. But what if we thought of all the ones which did commute with C and we formed a set out of those? Well, you have 2 jobs here. One, I want you, well, part A, excuse me, I want you to show that that is indeed a subspace of R 2 by 2. And what do I mean by subspace? You have to show it's closed. It's closed under addition, and it's closed under scalar multiplication. If you take 2 things out of S and you add them together, are they still in S? If you take 1 thing out of S and you multiply it by a scalar, is that result still in S? That's the question. And then the next part of that, well, what's the dimension of this space? If it is indeed a subspace of R 2 by 2, and it's probably not all of R 2 by 2, right? Then it's probably some subspace and with a smaller dimension than R 2 by 2 has. R 2 by 2 has dimension 4. Earlier we wrote down 4 basis vectors for it. So the dimension of S is something probably less than 4. And that's the exercise. Why don't you figure out what that is? Here's a hint. I think you should probably start by saying that A is equal to this, and then if it has to commute with C, see what you can figure out about the numbers A, B, C, and D. Have fun.